Yes,
Okay,
perfect.
very good. So yeah, welcome to my talk. I'm going to talk a bit about the performance of the Belle II tracking using collision data. Just a short summary about our experiment, as not everybody might be familiar with it. The Belle II detector is installed at the Super CTD2020 accelerator. It's an asymmetric E plus E minus B factory to study CP violation in rare decays. The center of mass energy is chosen right above the mass of the epsilon 4s resonance at about 10.6 GeV. And well, this is done since this resonance almost exclusively decays to a pair of B mesons. The peak luminosity is about 40 times higher than the one from the CTD2020, so the predecessor accelerator installed there, up to 8 times 10 to the 35 per square centimeter second. We achieved that by a significant reduction of the beam size. So we have something that we call the nanobeam scheme, and of course, higher beam currents. The goal, so until the end of the lifetime, basically, we want to collect data that corresponds to 50 inverse autobahns. So we're not quite there yet. I mean, we just started collecting data last year. So right now we collected about 25 inverse femtobahns. And the challenges that we're currently facing that we have to increase the instantaneous luminosity. And in order to be able to do that, we have to reduce the beam backgrounds. Yeah, a few words about our detector. The Belle II experiment is actually a significant upgrade, even though the name might suggest otherwise. The new detector design is motivated by the high instantaneous luminosity and the challenges that come with it. And apart from that, it's yeah, more or less standard detector. So in the center, you have the vertex detectors and the drift chamber, which makes out most of the tracking volume. Then we have detectors for particle identification, an electromagnetic calorimeter, and on the very outside, a designated detector for K-longs and muons. Yeah, a few more words about the tracking detectors here. So in the very center, shown by the light blue arrows here, you have the pixel detector, or short PXD. Out of the 2 layers, well, of the second layer right now, there are only 2 layers installed, the rest will come later. And the main task of the PXD is a precision measurement of the impact parameter. And it's actually pretty good in doing so, as the first layer is installed at a radius of just 1.4 centimeter. Hardware-wise, it's based on a depth-fed pixel technology, and one of the advantages is the very low material budget of just 0.2% of a radiation length. Then this is surrounded by 4 layers of the SVD, our silicon vertex detector. The SVD allows for very robust tracking despite the background levels that we have, and it's also a very good standalone tracking detector, actually. Hardware-wise, it's a double-sided silicon strip detector. Again, very low material budget, just 0.7% of a radiation length. And also the excellent hit time resolution allows us to suppress the backgrounds. All of that is then surrounded by our drift chamber, the central drift chamber CDC. It's 56 layers of wires that are grouped in alternating super layers of axial and stereo wires. Stereo wires are wires that are skewed by an angle with respect to the direction of the beam, so we can measure the C position of the tracks as well. The CDC is especially important for the momentum resolution, as it covers the tracking volume of up to a radius of 2.2 meters. Yeah, the properties of these epsilon 4s events and the tracking challenges that we're facing are summarized in this slide here a bit. So in a typical epsilon 4s event, we expect about 11 tracks at quite a soft momentum spectrum. So you can have a look at this figure here, and you can see that most of the tracks are in the momentum range between 0.3 and 0.6 GeV or so. So this is really low, especially compared to the LHC experiments, of course. And most of the tracks are like this green one here, which are tracks from charged pions. So about 73%. And all of that comes in quite a difficult surrounding. So we have high machine background, and the number of background hits are about 2 orders of magnitude larger than the actual signal hits. Analysis-wise, for us, it's very important to have a precise measurement of the primary and secondary vertices. And so if you want to study CP violation, you basically want to measure the flight distance of the B mesons, as this directly translates to the lifetime. And given the boost that we have here in our experiment, the flight distance is in the order of 10 to 100 micrometers. Furthermore, many of the analyses use a technique that we call full event reconstruction. And you can basically think that what we want to do is that to reconstruct the whole decay chain of the B mesons with all the intermediate particles and so on. And to be able to do that, we have to find every single track in the event down to momentum of about 50 MeV or so. And well, that's without reconstructing any fake or duplicate tracks. Yeah, before we can get started with the actual tracking, we have to suppress the background hits. As an example here, I picked the background in the CDC in our drift chamber. And well, we want to reject the background while still preserving the signal hits. And in the CDC, we do quite more or less classical approach there. We require a minimum of the deposited charge and time over threshold, and this actually works very well. Furthermore, we observe something that we call crosstalk, and this means that the neighboring channels in the readout chips can also light up if you register a signal hit, but these additional hits have a small charge and peculiar time structure, so we implemented a designated filter to target that topology. Yeah, now coming to the tracking algorithms that we use. All of what we do is summarized in this block diagram here on the left side. It's quite complicated, there's quite a lot of happening there, but just looking at these different blocks here, you can see that it's a very modular system, and we can actually restructure the track finding sequence in case it's needed. So we can adapt it to the background conditions, to the degradation of the detector, and so on. Yeah, to give you a brief overview of what is happening when and where, you can have a look at the small sketch here on the bottom. So the first step of the algorithm, we start in the CDC, in the drift chamber, then we go to the SVD. In the third step, then we start in the SVD again, go outside to the CDC. This fourth step actually has just recently been added, which is again one of the advantages of this smaller system. And in the very end, everything that we found so far is extrapolated to the PXD. Yeah, on the following slides, I'll go into a bit more detail about each of these algorithms. But if you're really interested in what we're doing here, I can suggest you should have a look at our Belle II tracking paper that has just recently been submitted. Yeah, so first step is the CDC track finding, and this actually consists of 2 algorithms. The first one is a global approach based on Legendre parameters. So we start considering axial wires only. In the first step, the C information is then added in the very end. And if you look at this figure here, so this dashed line corresponds to the particle's trajectory, and the hit positions can be approximated by the drift circles around the wires. In the second step then, we apply a conformal transformation that transforms the circular trajectory to a straight line, while the drift circles stay circles, and this simplifies the problem quite a bit, because now we have to find a tangent for a set of circles. To do that, we use Legendre parameters to describe these drift circles. So you have this equation here where the Legendre parameters are theta and rho here. And if you plot that function for each of the drift circles, you arrive at this figure down there, where each of the curves basically corresponds to one circle. And now you have to find points of maximum density in the phase space. And this is typically done using a 2D binary search. We're actually very proud of the implementation there. we have a dedicated quad tree structure, and we have something that we call sliding bins, where you basically recenter these bins to the points of maximum density in this phase space. The second track finding algorithm, again, this still takes place in the CDC, so we're still at the first step here, is a more local approach that is based on a cellular automaton, and that is good for reconstructing short and displaced tracks. So in the first step here, we are combining triplets of hits in neighboring layers here, assuming a certain right-left passage. In the second step, we are trying to connect the triplets that share 2 hits and assign a weight on that based on a common fit to both segments here. And in the final step, then in the bottom, we combine overlapping segments and calculate a weight again. Currently, we're actually not using this as a standalone tracking algorithm due to the non-negligible fake rate. So all that we do at the moment is that segments found by this algorithm are added to tracks that we found in the previous step, so with this global track finder. After the combination, then in the very end, there are several further MVA-based filters to improve the fake encoding rate, as well as purity and track parameter resolution. Just to give you a bit of an outlook here, so currently we are studying an additional track quality indicator that can reduce the fake rate of this local track finder, so we can actually use it as a standalone algorithm. So in the next step, then we're trying to extrapolate these tracks that we found in the CDC to the SVD, and we do that with a combinatorial Kalman filter. So yeah, we start from these CDC tracks, we extrapolate them inwards toward the SVD layers. The algorithm may actually skip 1 or 2 of these layers to account for inefficiencies, and then we're trying to find all hits in a certain window around here, this extrapolated track position, and we pick the best of these hit candidates using MVA-based filters. We then define a new path based on all the candidates that we selected and repeat the procedure for each of them. And then after repeating that until we arrive at the very center here, we select the best candidate for each of the track seeds here. A few words about the implementation again. It's highly configurable, so it's purely template-based. We use a lot what we call filters that we use to select the best hit and path candidates, and these can be modified and tuned easily. And due to that template-based nature here, we can use the exact same code in the very last step, so here in step number 6, where we extrapolate all the tracks to the PXD. Yeah, just a remark again here, we currently do not consider material interactions during the CKF, as we have to do many extrapolations, and that is just a bit time consuming. But there are studies going on where we're studying to replace GenFit2, that is the tracking toolkit that we use with ACTS, which is actually faster when modeling material. Then, yeah, coming to the third step, this is our SVD standalone track finding. This is then basically you select all the SVD hits that weren't used by the second step and try to find tracks there. And this algorithm is based on a concept that we call sector map that stores friendship relations between the sensors, where each of the sensors is split in 3 by 3 sectors. And we define this friend relation using simulated events. And whenever you have a track in a simulated event that passes to 2 consecutive sectors here, you then define a friends relation. This greatly reduces the complexity of the track finding problem by lowering the potential combination of hit points. And we can actually tune the granularity of the sectors for high efficiency and low fake rate. To then actually find the tracks, we again use a cellular automaton based on pairs of space points that have this friends relation. We have a couple of filters that reject bad combinations, so the requirements on the angle and timing and so on. And in the end, there's an MVA that rejects fake and clone tracks. A few words about the performance. This works very well. This algorithm is basically a Belle II kind of invention, and it performs better than we anticipated. And yeah, we're very happy with it. Now advancing to step number 4, and this is the one that has just recently been added. And the reason why we did that is that forward tracks are sometimes not reconstructed in the CDC. So here in step number 1, they can have a low number of hits, and we have higher than expected background levels. However, the VXDTF2, so this is the SVD standalone tracking, manages to find a significant fraction of these tracks. The SVD has a larger acceptance, and it actually proved to be more robust against background, while we still want to add CDC hits to these tracks as they can improve the momentum resolution. To illustrate that a bit, I selected 2 track events in data, and in this top figure here, you can see the fraction of tracks that have CDC hits added to them as a function of tan lambda. That's basically the slope of the track. And you can see that especially in the forward regions here, the CDC track finding efficiency increases quite a bit. To then illustrate that this also improves the momentum resolution, you can have a look here at the bottom figure where I calculated the invariant mass of these 2 tracks. And you can clearly see that the peak gets more narrow here. Yeah, now after I introduced all the algorithms, a few words about the performance. So actually the track finding efficiency is quite robust against beam background. So looking at this figure here, you can see that the performance is still acceptable at twice the expected background level. So this is the green curve here. But I should still clearly stress here that there's a lot of room for improvements, as we haven't really done any optimizations for higher than the expected background levels. Also, the track parameter resolution is excellent. So on the left side here, you can see the resolution in the transverse impact parameter, D0. So this is in the micrometer region, and here on the right side, the relative momentum resolution, and also that looks very good. Yeah, now to give you a bit of an outlook, there are further developments going on where we're trying to add additional tracking algorithms. And this one here that I want to show you as an example, we call the ECLC.CKF. And the motivation here is that if you have a look at the track finding efficiency as a function of the particle type, you can see that track finding efficiency is like 5% lower or so compared to the other particles. And this is, of course, because of the additional material effects. So one of the ideas that we had is that we use showers in our calorimeter as seeds for combinatorial Kalman filter. And we expect this to increase the tracking efficiency, especially in the forward regions where the particles have to cross most material. The code development was quite easy, again, due to the template-based implementation of the CKF that we're using. And so what we do now is we do a helix extrapolation from the seed, so from out there to the center of the detector for both charge assumptions, and then we're trying to find hits along these extrapolations and arrive at a full track. The implementation is done, and currently we're optimizing the parameters of the CKF, and well, we still have to validate it on data. There's room for improvements, so you could actually add Bremsstrahlung photons to the track. You could try to find vertices from pair production and so on. So there's a lot of ideas that we have. Now slowly advancing to data. This is a short slide about the performance on the high-level trigger. Tracking is running very stable. We're very happy with that. And looking at the average timing here, you can see that, well, as expected, tracking is the most time-consuming process. We need about 1 second per event on a single core. Most time-consuming are the CDC tracking, the track fitting, and the vertexing. Still, numbers are okay, so this is not critical at the current conditions, but the computing time will rise at higher background levels, of course. Still, we're not quite worried. There's room for improvements. As I mentioned, we started to replace this GenFit2 toolkit with ACTS. and this should also provide a faster fitting, and we can always restructure the track finding chain due to the modularity that we have to optimize that a bit more. Okay, yeah, now advancing to data, one of the things that of course you always have to do is to compare your simulation to data. And for us, the track finding efficiency is really essential. It's really a key performance driver for Belle II physics, simply because we have all these analyses where you tried to reconstruct every single decay in the event. So there is a large variety of tag and probe studies going on to validate the efficiency for different momentum ranges. Here on the slide, you can see 3 of the final states that we use to validate that. And as an example, I picked the one here in the middle, and I talk a bit more about that. So for this intermediate momentum ranges, we exploit tau pair events where your tag is 3 good quality tracks with a total charge of ±1. And then you have your probe track here that passes a loose selection and conserves the total charge. And then you can count the number of events where the probe track is found or not. And this gives you an estimate of your track finding efficiency. Yeah, unfortunately, I can't provide you with any numbers, but you can have a look at this histogram here, and you can see that these results nicely line up with 0 here. So the study shows a high level of agreement between data and simulation. Yeah, now some other tasks that we do all the time. This is the monitoring of the beam spot width, and we control the alignment that we're doing. Yeah, just to make you a bit more familiar with the beam profile that we have. So for this high luminosity, we have a strongly squeezed beam in the vertical direction. So sigma y here is less than 2 micrometers, while in x direction it's about 15 micrometers or so. And you can measure this D0, you can measure the impact parameter of the tracks. Here in blue, we did it ignoring the PXD basically, so just CTC and SVD. And in red, we add in the PXD. And well, obviously, the PXD significantly increases the impact parameter resolution, and it's determined to be about 12 micrometers. So this is a really nice performance, and we are very happy with that. Furthermore, the good alignment, of course, is a key ingredient to the tracking. Otherwise, things like that wouldn't be possible. And we do that with the Millipede 2 framework. Yeah, a few more words about the beam spot. So you can also measure the D0 distribution as a function of the phi angle here. And you expect this camel kind of shape here. And that simply comes from the fact that our beam spot is not symmetric, as I just showed you. And so this is the distributions that we measure in simulation and data. And if you unfold it using the D0 resolution I showed you in the previous slide, you end up with this distribution down here, which is basically an estimate for the beam profile. And here, data and simulation align nicely. So again, this shows the excellent performance of our tracking and alignment. Yeah, now coming to my final real slide here. And this is a bit of a highlight. This is the measurement of the D0 lifetime. This is a highly track-based analysis, and as such is an excellent exercise to test the vertexing and alignment. Well, obviously, apart from the physics aspect, there is. So we select a very pure sample of D star plus to D0 pi plus candidates with the D0 reconstructed in 3 different final states. I pick one of them here, this one, and this is the D0 lifetime that we measure in data. So this plot unfortunately has very poor statistics, but I cannot show you any others, unfortunately. But you can clearly see this exponential decay here, and this confirms the excellent resolution that we achieve with our Belle II tracking detectors. So all in all, these first and still preliminary studies are compatible with the expectations, and they illustrate the good performance of our tracking detectors and algorithms and also alignment. So yeah, now coming to my summary, we really observe an excellent performance of our tracking detectors and algorithms. This high flexibility of the modular approach proves to be quite advantageous to adjust tracking to the background conditions and performance requirements, and it's quite easy to add in additional algorithms and so on. There are many studies going on trying to exploit MBA-based approaches for all kinds of use cases, so background rejection, track quality, etc. And the first tracking-focused studies and analysis that we're doing show really promising results. And thank you. That's it from me.
Thanks a lot, Simon. Any questions to Simon? Jenny, I see your hand.
Yes, hello. Can you hear me?
Yes.
Yes, we can.
Ah, perfect. So I was a bit interested about in the fake rate for the cellular automaton. Mm-hmm. So do you have, you said that there will be work to decrease this, and do you already have some ideas what to use for evaluating what could be a good tractor and not for using the cellular automaton as a standalone tracker?
So we implemented an additional quality indicator that is purely based on the track properties and properties of the hits. It's based on fast BDT. We have some preliminary results that are very promising, and we managed to reduce the fake rates down to, wait, I might actually have a slide in the backup now that I think about it.
Okay.
So here it is. This is the fake rate. These teal dots is the fake rate of this with the cellular automaton. And you can see by cutting on this quality indicator, you can reduce it from like a 10% level down to 3% level, so that we currently have. And all of that, while the finding efficiency in this bottom figure here is still higher than the nominal one, so the one that we have at the moment.
Okay.
But again, this is preliminary studies, and the results might actually be better than what I'm showing you here right now.
Mm. Okay, thank you.
Okay, no other questions? Joe as well.
Yeah, hi. I was just wondering if you could comment on your progress with implementing the ACTS track fitting.
So we had someone working on that for a while, but he unfortunately left physics. And there is a new PhD student that started taking over his work, but he just started like a month ago or so. So I think we should talk again about that in like a month or two. And but we're working on that. The results that we had from Niels, the previous student, it looks very nice. And yeah, so yeah, that's all I can say at the moment.
That's fair. I was just curious. I'll talk later today about trying to implement ACTS in the S-Phoenix experiment. So I was wondering if maybe there was potential for us to collaborate in some way on that. But just thought I'd ask. Thank you.
Yeah.
Thank you. But I think we have to move on. Simon, can you, by the way, upload your slide to Antico?
I cannot, unfortunately, because I don't have a CERN account. Apparently, I need a CERN Indico account to do that.
Yeah, we can sort this out. Please send an email to me. Well, yeah. David also at CERN.th.
Yeah, I will.